We are all brought up to understand that the air we breathe, the water we drink, the earth we stand upon, and we ourselves are all made of almost unimaginably small particles that we call atoms. The largest atom is less than 1/millionth of 1 millimeter in diameter. To put that in some kind of perspective, if you wanted to cover an A4 page with a single layer of carbon atoms, the number you would need would be similar to the number of grapes you would need to cover the entire surface of the Earth. The diameter of an atom is around 1,000 times smaller than the wavelength of visible light, and that means that even with the most powerful optical microscope, we couldn't come close to seeing an individual atom. Today, technologies have been developed that can generate images which are resolved down to that incredibly small scale, and they do indeed reveal the presence of individual atoms. But this is very much 21st century technology. So the question is, how did the idea of atoms come to be so widely accepted long before we could visualize them anywhere other than in our heads? The idea actually is extremely old. It goes back once again to ancient Greece. In the 5th century BCE, although they had very little science to go on, philosophers were already thinking hard about how the universe worked. And two things they were uncomfortable with were infinity and nothing. They didn't like the idea of anything that appeared to have no limit. And this came up in the context of cutting a material in half, and then in half again and again and again. And they saw that there seemed to be no limit as to how small the particles were that you could generate as a result. They were equally troubled by the concept of empty space, the void. If a space had nothing in it, then, they argued, by definition, it didn't exist. But if there was no such thing as an empty space, then movement must be impossible, because something couldn't move unless there were an empty space for it to move into. And therefore they ended up, some of them at least, concluding that all movement was nothing but an illusion. Leucippus and Democritus weren't having any of this. They came up with an idea which they felt addressed both of these problems. They proposed that all matter was made up of particles so small that you couldn't see them individually, but not infinitely small. And they proposed that these particles were indivisible, so they represented a lower limit on how small you could go when you were cutting things into bits. The word for indivisible in the language of the time was atomos, and that is the origin of our word atom. They further argued that these atoms were constantly in motion, and therefore the void was not the troublesome nothing that had caused all these philosophical problems, but rather it was the space that was needed for the atoms to move around in. So they developed a whole quite complicated story about atoms and how their behaviour might give rise to the things that we observe in the world on the human scale. The atoms, they argued, would move around randomly in the void and occasionally collide with one another. And when they did, they might simply bounce off, but sometimes they would stick together. And that could lead to assembly of larger, more complicated structures, culminating ultimately in the objects that we can see and touch. This is actually remarkably prescient of the modern scientific view. But we should be clear that all of this was philosophy, and that's not the same as science. Both of them depend on logical thinking, but in the end, the validity of a philosophical idea is tested against pure reason, whereas science demands that an idea can be validated only through observation and experiment. In ancient Greece, even if they had the inclination, they certainly didn't have the technology that would be needed to find empirical evidence to support their atomic model. Nevertheless, the idea of atoms was out there, and it did arouse a lot of interest, but it was never accepted as mainstream. Aristotle didn't like it, and what he thought was for a long time seen as the gold standard for what was likely to be true. Nevertheless, the idea didn't disappear, and it was still there more than 2,000 years later when Daniel Bernoulli arrived on the scene. Bernoulli was a Swiss scientist who was fascinated by gases and how they move. He was the person, for example, who explained how birds can fly in terms of the shape of their wings and the vertical pressure differential this creates as they move through the air. It occurred to Bernoulli that it might be possible to understand gas pressure in terms of atoms moving around randomly in the void and exerting a force on whatever object they might happen to crash into. But Bernoulli was a scientist. He wasn't going to take this view seriously unless he could find empirical evidence for it. Now, by this time in history, there was a lot of data out there about how gas pressure varied with volume and temperature. And what Bernoulli found was that he was able to predict this behavior by taking Isaac Newton's equations of motion and ideas about momentum and kinetic energy and applying them in a model system where a bunch of atoms moved around randomly in a container. This, on its own, was not enough to convince many people of the atomic theory still, but it did mean that for the first time the theory had been tested against scientific measurements and had passed. One thing that can really help a scientific theory gain traction is when two quite different lines of evidence converge in its support, because this helps remove that nagging doubt that everyone might be working with the same wrong preconceptions and assumptions. And this is what happened for the atomic theory more than half a century after Bernoulli's work, when a Manchester chemist called John Dalton produced new, compelling, albeit still circumstantial evidence for the existence of atoms, based this time on chemical rather than physical measurements. At this time, chemistry was pretty much a branch of cookery. A great many substances had been discovered, and they had learnt how to combine and transform them to produce new substances. But there was very little understanding of what was going on, and Dalton was determined to change this. He became fascinated by the ratio of the masses of different elements which could combine to form compounds. For example, it was known that carbon could form two different gases in combination with oxygen. If you take 3 grams of carbon, it can combine with 4 grams of oxygen to form poisonous gas that can kill you if you have too little ventilation around your fire. Or your 3 grams of carbon can combine with exactly twice as much oxygen, 8 grams, to form the very different gas that we exhale from our lungs. Dalton pondered this and came up eventually with the idea that it happens because elements are made up of atoms. Each atom of the same element has the same weight, but atoms of different elements have different weights. And groups of these atoms in specific numbers then combine together to form molecules of compounds. So, in our case, if 1 atom of carbon combines with 1 atom of oxygen, you get a molecule of that poisonous gas, which we now call carbon monoxide. Whereas if 1 atom of carbon combines with 2 atoms of oxygen, you get a molecule of that gas that we breathe out, which we now call carbon dioxide. Dalton extended this to a bunch of different elements and found similar patterns of behavior in each case. And when he published the work, he was able to include a list of the relative atomic weights of all of the elements that he had studied. This work was greeted with great enthusiasm by other chemists, who joined in measuring the atomic weights of other elements, correcting some of the oversimplifications in Dalton's original work, and beginning to develop a theory of compound formation. By the middle of the 19th century, chemists were starting to draw pictures of how atoms might be connected up to form molecules. And when, in the 1860s, Mendeleev arrived at his first periodic table, in which he used the atomic weights to order the elements correctly, the atomic theory was firmly established as the basis of all modern chemistry. In the physics community, though, opinion about the atomic theory remained much more divided. Some thought it was just a mathematical device which chemists had invented to explain their data because they didn't really understand what was going on. And others objected in principle to any theory that was based on something that seemed to be fundamentally unobservable, such as an atom. There were others, however, including two of the great minds of 19th century physics, James Clerk Maxwell and Ludwig Boltzmann, who were prepared to take the idea seriously and who set about exploring its ramifications. If you think about balls on a snooker table, you know that when particles collide, energy is transferred, so that one invariably slows down and the other speeds up. This would be true similarly for atoms or molecules moving around randomly in a gas and colliding with one another. And the consequence is that a question like what is the speed of a molecule in the gas is meaningless because they will all have different speeds, and the speed of any one molecule will be changing constantly from one collision to the next. Maxwell and Boltzmann independently realized that this meant the only way that you could really understand the physics of a system made up of atoms and molecules was to apply the laws of statistics. But this was a scary notion because it seems to imply a degree of unpredictability. Think about what happens if you flip a coin 10 times. The statistically most likely outcome is that you'll get 5 heads and 5 tails. But if you were to get 7 heads and 3 tails, you wouldn't be shocked. You just shrug your shoulders and say, well, that's the kind of thing that can happen by chance. So does that mean that the properties of a gas, like say its pressure, might fluctuate from one minute to the next, just depending on changes in the distribution of energy amongst the molecules? Clearly this is not what happens in the real world, so if this is what the model predicted, there would be a problem. Now think, however, about what would happen if you flipped that coin 10,000 times. If you got the same ratio, 7,000 heads and 3,000 tails, now you would be deeply suspicious about there being something dodgy about the coin. The point is that the bigger the number of individual contributions to your distribution, the more confident you can be that the distribution will be close to the statistically most likely one. And because atoms are so tiny, they are extremely numerous in any sample of a reasonable size. Every time you breathe, you inhale around 25 billion trillion molecules. And that number is so huge that it means the energy distribution in that sample will conform almost exactly to that statistical prediction. Realizing this, Maxwell and Boltzmann were able to derive equations which we now know describe almost perfectly the energy distribution among the molecules in a gas, although at the time that was not directly testable by experiment. Boltzmann and others went on to show that everything that was known about thermodynamics, which is the physics of heat and work and energy, was explicable in terms of this statistical theory of atoms. There were many people, however, who still rejected the theory because it was founded on atoms, the existence of which had still not been demonstrated. In 1905, Ludwig Boltzmann ended his own life. His mental health had always been fragile, and we'll never know quite what was going through his head that day. But his despair that the work he'd put together over 40 years was considered by many of his colleagues to be just an elaborate work of fiction surely played a part. That powerful skepticism, which is so crucial to keeping science on the right track, carries with it a price. And the stereotype of a scientist as an analytical, unemotional figure is clearly a silly caricature. Ironically, the observation that would in the end provide the experimental vindication of the atomic theory had already been made before Ludwig Boltzmann was born. In 1827, the Scottish botanist Robert Brown was observing pollen grains suspended in a drop of water under a microscope. And he noticed that tiny particles shed by some of the pollen grains seemed to move around, performing a strange random walk in which they constantly changed direction, apparently of their own accord. He thought they might be alive, so he did what a good scientist does, a control experiment. He replaced the pollen with fine grains of an inorganic mineral and observed the same thing. Clearly, there was something unseen which was pushing these particles around. It wasn't until the turn of the 20th century, though, that this work started to attract the attention of physicists. But in 1905, Albert Einstein hypothesized that the particles were moving because they were being buffeted by the numerous unseen water molecules surrounding them. He devised a statistical model for this behavior and derived an equation which made experimentally testable predictions of features of the random walk that should result. And just 3 years later, Jean Perrin published the results of very careful experiments which were in close agreement with Einstein's equations. This combination of theory with experiment finally convinced almost everyone that statistical physics was valid and that atoms were real. Boltzmann, sadly, had died 2 years previously. While it was their chaotic, random movements in a liquid which convinced many people of the reality of molecules, it's the other side of the coin, the ability of atoms to bond together in non-random ways to form molecules, and in turn of these molecules to interact with one another, that gives rise to the richness and diversity of the material world around us, and indeed that makes life possible. By this time, chemists had learned a great deal about this behavior. But none of this understanding was based on actual observations made on the atomic scale. Rather, it was inferred from physical measurements and patterns of chemical reactivity observed on the everyday human scale. So, while the interactions of atoms and molecules were very real in the minds of the chemists, the challenge remained to find methods which could actually detect them. Because they are so tiny, this has required phenomenal ingenuity. Scientists are sometimes portrayed as analytical people lacking in imagination and creativity. But when you understand the tricks that they've come up with to get around this problem, you realize that this is total nonsense. Today, pictures of the structures of complex molecules, showing in detail the interactions between the different atoms, are very familiar. Most people know, for example, the beautiful double helical structure of DNA. But these are not images of individual molecules. Most of them were obtained by X-ray crystallography, which is a technique involving firing a beam of X-rays at a crystal containing a huge number of molecules arranged in a regular way. from the pattern of scattering of the X-rays observed, a mathematical analysis can be used to infer how the individual atoms are arranged within a molecule. This technique was invented by Lawrence Bragg and his father in 1913, and it's been spectacularly successful in, for example, revealing how life processes work at the molecular level. Nevertheless, actually obtaining an image of a single individual atom remained a challenge. It was finally achieved by Erwin Müller in 1955. He built a device called a field ion microscope, which has an extremely sharp metal tip surrounded by helium gas. He used a high voltage to make the tip positively charged and to turn the surrounding helium atoms into positive ions. Then, because like charges repel each other, these ions flew away from the tip, and because the tip had a slightly curved contour, they diverged as they did so. Some distance away, he then had a screen which could detect the arrival of the stream of helium ions. Because the metal tip had a slightly curved contour, the ions diverged as they moved away from it. And so, what formed on the screen was a magnified image of the tip. It's a bit like shadow puppetry, where light from a lamp diverges as it moves away, and if you place your hand in front of it, you can create a magnified image of the hand on the wall some distance away. The magnification that Müller could achieve using this technique was so great that he was able to resolve individual atoms on the surface of the tip. Today, we have the atomic force microscope, which uses the idea that although we can't see individual atoms, we can feel them. A very fine probe is dragged systematically across the surface and responds to the force it feels when it encounters bumps along the way. And as the technique has become more refined, it's become possible to pick up bumps as small as individual atoms. In 2018 at Oxford University, a photograph was taken which became slightly famous as the first photograph of a single atom taken with an ordinary camera. They turned some strontium atoms into positive ions and then were able to trap one of them in an electric field at a very low temperature. Then they excited this ion by shining a laser on it, and in response the ion emitted blue-violet light, and a long exposure photograph detected this as a faint blue dot. Of course, it's a bit of a cheat, really. It's not an image of the individual ion. Rather, it's a single pixel in the camera responding to the region of space where the ion was localized. Nevertheless, it's as close as we're likely to come to seeing an individual atom. Leucippus and Democritus and Bernoulli and Dalton and Maxwell and Boltzmann and all the rest would have been proud. Today, we know, of course, that atoms are not the simple, indivisible structures that they were originally assumed to be, and working out the detail of what's going on at the subatomic level was to prove another great challenge. But that is another story.